Why does everything fall down? It seems like a simple question. You drop your keys, they fall. You leap into the air, you come back down, usually less gracefully than you left. But this ordinary, reliable experience hides something far stranger. Gravity isn't just about keeping your tea on the table. It's one of the most quietly powerful forces shaping the universe itself. Tonight, we'll explore how gravity works. Not just how it makes things fall, but how it bends space, moves planets, and decides the fate of stars. We'll start with what you already know, even if you don't realize it. Then, gently, we'll peel back the layers until we're staring into the heart of black holes and the edges of what science can currently explain. Gravity, as it turns out, is both familiar and profoundly mysterious. It's the weakest of the four fundamental forces in physics, and yet it holds entire galaxies together. It sculpts the cosmos, determines the passage of time, and quite literally warps the fabric of space. Not bad for something that also makes apples inconveniently bruise themselves. You might assume we've got gravity all figured out. After all, Newton did the apple thing. Einstein came along with some equations, and now we've got satellites that tell us where to go and when to turn left. But the truth is, we still don't fully understand what gravity is. We know how it behaves, we can measure it. But the deeper questions remain. Tonight we'll explore how humans first noticed gravity, how we tried to explain it, and how our understanding has evolved. Sometimes slowly, sometimes in giant leaps. From ancient stargazers to physicists firing lasers at the moon, it's been a long and patient journey. We'll see how gravity works, not just here on Earth, but on the moon, in the orbits of planets, around black holes, and across billions of light years of space. We'll talk about space-time, quantum weirdness, entropy, and yes, how it all eventually leads to the heat death of the universe. Cheerful stuff. Sleep tight. By the end, you'll understand why gravity is both comforting and completely indifferent. It holds you in place, keeps the moon in the sky, and shapes the universe. All without so much as a raised eyebrow. If gravity had a personality, it would be the sort of person who shows up, does their job perfectly, and leaves without speaking to anyone. This leads us to consider the central mystery. If gravity is everywhere, why do we still find it so hard to explain? So then, what is gravity? Not what it does, but what it is. That's the question. A question so ordinary you've probably never asked it out loud, and yet so complicated that physicists have spent centuries trying, and mostly failing, to answer it. Everything falls. Yes. But why? We're used to thinking of gravity as something obvious. You let go of a pen, it drops. If it floated away, you'd panic. Or assume you were dreaming. Gravity feels like a basic setting on the universe, like the on switch for reality. But once you ask why it works the way it does, things become less clear and much stranger. There's the version we get in school, that gravity is a force pulling masses together. And it's not wrong, exactly, it's just not the whole story. Because when we try to look closer, to ask what causes that pull, the answers become less like solid explanations and more like increasingly polite guesses. It turns out gravity is the least understood of the fundamental forces in physics. Electromagnetism, sorted. The strong and weak nuclear forces, we've got equations. But gravity still sits in the corner of the room, refusing to explain itself. Like a teenager who's decided they're above family conversations. Tonight, we'll ask the question properly. What is gravity? not just in the way it affects us here on Earth, but across time, space, and scale. How does it govern the motion of planets, shape the universe, and even affect the passage of time itself? And perhaps most importantly, why do we still not fully understand it? We'll look at how gravity influences everything from the fall of an apple to the merging of black holes. We'll trace how people have tried to understand it, from ancient ideas to modern physics, and we'll see how each explanation answered old questions while raising entirely new ones. That's the thing with science. Just when you think you've nailed it, nature reminds you you've still got the IKEA instructions upside down. But this isn't about being clever for the sake of it. Understanding gravity means understanding something about reality itself, about how space works, about how time flows, about how the universe behaves, even in the farthest reaches we'll never visit. This leads us to consider our own direct experience, the familiar pull of gravity we feel each day, and why our instincts about it, while useful, might not tell us the whole truth. You feel it constantly. The pull of gravity. It presses your body into the bed. It's the reason your arms get tired holding up your phone. It's why your toast always lands face down, especially if you've already made tea. Gravity is so normal, so expected, that most of us stop thinking about it by the time we're out of primary school. And yet, it affects almost everything you do. You walk, not float. You sleep lying down, not hovering near the ceiling. When you drop your keys, you know exactly what will happen. They'll hit the floor. They don't shoot sideways or hang in the air waiting for a decision. Gravity always pulls down, like the universe is a bit obsessed with keeping things grounded. It's one of the few things in life that works the same way every time. Whether you're on a mountain, in a city, or tripping over a shoe you swore you moved yesterday. Gravity never misses its cue. It doesn't matter if you're a person, a cat, or a cup of tea. Let go, and down you go. Predictable, reliable, utterly unquestioned. But here's the thing. You can't see gravity. You feel its effects, but you'll never catch it in the act. There are no gravity particles you can hold, no visible ropes pulling things together. You've just grown up in a world where its behavior is so consistent, you trust it without needing proof. Which, incidentally, is more trust than most people give train timetables. What's interesting is that your natural instincts about gravity, while useful, are only part of the story. You know things fall, and you've got a solid grasp on up and down. But that's based on living on a large, round object with a massive core and a surrounding atmosphere. If you grew up on a tiny asteroid, your sense of normal would be very different, and so would your bone structure. In fact, your whole body is adapted to gravity. The strength of your muscles, the shape of your spine, even your inner ear, all designed by evolution to function in this ever-present downward pull. Take gravity away and you'd float, sure, but you'd also vomit, lose your balance, and slowly forget where your feet are supposed to go. So, even though gravity seems like background noise, always there, always working, it's one of the most crucial forces shaping your every movement, decision, and environment. And you're right to feel confident in it. After all, gravity has never taken a day off. This leads us to consider the world as we observe it, how gravity presents itself to our senses, and why those observations, while helpful, don't tell the whole truth. You watch a mug fall off a table and smash on the kitchen floor. You don't stop to ask why it fell. You just reach for the dustpan and mentally add mug to your next shopping list. but what we observe in moments like that forms the basis of how we think gravity works. Things fall, and heavier things fall harder. It seems straightforward. From a young age, we build a mental picture of the world based on what we see, hear, and feel. You throw a ball, it arcs and lands. You jump, you land. Drop something, it drops. So naturally, we assume gravity is simply a force that pulls things down. It works the same way every time, so we rarely question the details. And that's fair. Most of the time, this instinct works. But our senses only show us part of the picture. The ground feels flat, even though the earth is round. The sun seems to move across the sky, when in fact, we're the ones spinning. Our eyes and ears are tuned for survival, not scientific accuracy. So when it comes to gravity, what we see isn't always what's actually happening. Take weight, for example. You might think your weight is just how heavy you are, but it's really the force gravity exerts on your mass. Your mass, the amount of matter in your body, doesn't change. But your weight does, depending on how strong gravity is where you are. Stand on the moon, and you'll weigh about a sixth of what you do on Earth, which is why astronauts bounce instead of walk. It's not the boots, it's the gravity. Or, consider free fall. It feels like falling is caused by gravity, pulling things down. But from a physics point of view, falling is what things do when nothing else stops them. Gravity isn't dragging objects to the ground. It's simply the reason they move that way once they're not being held or supported. And once you remove air resistance, like in a vacuum, a hammer and a feather fall at the same rate. Galileo worked that out in the 1600s. Some people still haven't got the memo. Even the idea of down is entirely relative. On Earth, down is toward the center of the planet. But in space, there is no down. Up and down are defined by gravity's pull. And outside of that pull, they become meaningless. So that trusty mental compass you've relied on your whole life, turns out, it only works on Earth. And barely that. What we experience day to day gives us a useful but limited picture. Our senses suggest that gravity is simple, constant, and one-directional. But these observations don't tell us how it works, or why it exists in the first place. This leads us to consider scale, and how gravity changes as we step beyond our immediate surroundings. You've seen gravity at work on Earth. It pulls you into your chair, holds buildings in place, and ensures that if you drop a biscuit, it will always land on the carpet, jam side down. But these familiar effects are just one version of gravity. To really understand it, we have to zoom out, far beyond the scale of human experience. Let's start with something larger than your living room, the moon. It doesn't fall to Earth, nor does it fly off into space. Instead, it orbits in a delicate balance. Gravity provides the inward pull, and the moon's forward motion prevents it from crashing down. It's like perpetual falling, but sideways, which is quite a talent if you think about it. Go further, and gravity becomes the reason planets orbit the sun. It's not just that the sun is massive, though it is, containing 99.8% of all the mass in the solar system. It's that gravity's strength increases with mass, and it pulls over vast distances. Even though the sun is 150 million kilometers away, it still tugs firmly on Earth, keeping us in a stable orbit. No strings required. Now, scale up again. Entire solar systems orbit the centers of galaxies, drawn by the gravity of hundreds of billions of stars, dust clouds, and, as far as we can tell, something invisible called dark matter. Gravity doesn't care if it can be seen. It just acts, consistently, across light years, without fuss. And yet, gravity is also acting at tiny scales. Every object with mass, no matter how small, exerts a gravitational pull on every other. You are currently pulling very slightly on the person nearest to you. Don't worry, they're probably ignoring it, just like they ignored your last text. Still, the force is there, measurable with enough sensitivity, even if utterly insignificant in daily life. This is one of gravity's peculiar qualities. It is by far the weakest of the fundamental forces. Weaker than electromagnetism, and weaker than the strong and weak nuclear forces. And yet, unlike those others, gravity always attracts, never cancels itself out, and works across any distance. This makes it the dominant force at large scales, even though it's practically useless for holding your socks together. So, when we think of gravity as just falling, we miss the bigger picture. Gravity is the reason galaxies form, planets stay in orbit, and time behaves strangely near massive objects. Its influence stretches from your tea mug to the edge of the observable universe. Quiet, constant, everywhere. This leads us to consider how we actually explain gravity, not just observe it, and how the mechanism begins to reveal itself through science. After centuries of watching apples fall, moons orbit, and planets wander the sky, someone finally asked, "Can we describe gravity with numbers?" That someone was Isaac Newton, who, in the 17th century, managed to do something few people ever achieve: make apples more interesting than pie. He proposed that every object with mass pulls on every other, with a force we now call gravity. Newton's idea was simple enough to write down, but powerful enough to predict planetary orbits. His law of universal gravitation states that the force between two objects depends on their masses and the distance between them. Double the mass, and the force doubles. Double the distance, and the force becomes a quarter. It's a tidy equation. The sort of thing maths teachers get genuinely excited about. Importantly, Newton didn't explain why gravity works. He just gave us a way to calculate what it does. That was enough to guide centuries of physics and engineering. Using his equations, we could launch cannonballs, not a personal recommendation, chart the movements of planets, and even start planning to leave Earth entirely. For a while, gravity looked like it had been solved. Newton's model assumes that gravity is a force acting instantly at a distance, that one object somehow knows another is there and pulls on it without delay. At the time, no one had a better idea. It worked well enough. But as scientists looked more closely, especially at things moving very fast or very far, the cracks began to show. For example, Newton's equations couldn't quite account for the precise orbit of Mercury. It was close, but not exact, and physics, as a rule, doesn't enjoy being even slightly wrong. Like a sat-nav that insists you've reached your destination whilst you're very clearly in a lay-by next to a cow field. Despite that, Newton's model remains useful for most everyday cases: dropping a stone, launching a rocket, calculating tides. It gives accurate results. It's still taught and used widely because it's simpler than modern alternatives and good enough for most practical needs. But underneath that reliability, a deeper mechanism was waiting to be uncovered. The idea that gravity was a force, something pulling on things, was the best explanation available for centuries. But eventually, a new perspective was needed, one that didn't rely on invisible pulls acting across space, but instead redefined what space itself was doing. This leads us to consider a deeper process. How gravity, rather than being a force in the traditional sense, might actually be the result of something even more fundamental, the shape of space and time itself. By the early 20th century, Newton's tidy formula was showing its age. The maths still worked for apples and cannonballs, but as astronomers looked deeper into the skies, and physicists poked at the nature of light, something didn't quite add up. The universe was behaving like it had missed a few memos from Newton. Enter Albert Einstein with a rather different idea. Einstein's theory of general relativity, published in 1915, took the notion of gravity and flipped it sideways, quite literally. He proposed that gravity isn't a force pulling at a distance, but a result of mass curving the fabric of space and time. Large objects, like planets, stars, and black holes, bend the space around them. Smaller objects simply follow the curves, like a marble rolling along a stretched-out duvet. Now, the term space-time can sound a bit grand, as if it's trying to be both your geography teacher and your history teacher at once. But it's just the idea that space and time are linked, and that mass affects both. According to Einstein, the presence of mass changes the geometry of the universe, and objects respond by moving along the simplest paths available, known as geodesics. In other words, things move straight, but straight now means curved. This model helped explain all sorts of things Newton's couldn't. Mercury's orbit, for one. It shifts slightly each time it goes round the sun, and general relativity predicted that shift precisely. Light, too, bends when it passes near a massive object. This was confirmed in 1919 during a solar eclipse, when starlight passing near the sun was observed to be displaced, just as Einstein had predicted. Importantly, this wasn't gravity pulling on light, because light has no mass. Instead, the light was traveling along a curved path through distorted space. The space was bent, so the light bent with it. Gravity, in this view, isn't a force at all. It's geometry. If that feels like a cheat, you're not alone. But it works astonishingly well. Much like a sat-nav that somehow leads you correctly to a pub hidden behind 3 sheep and a stone wall. And the more mass something has, the more it bends space-time. Earth creates enough curvature to hold on to the moon. The sun curves space so much that the planets trace ellipses around it. Black holes, with enormous mass crammed into a tiny space, curve space so severely that not even light can escape. Einstein's view of gravity changed everything. It replaced force with curvature and action at a distance with local geometry. Space wasn't just a stage where physics played out. It became part of the action itself. This leads us to consider how this process holds across vastly different scales. From the tiniest particles to the largest cosmic structures, all governed by the same quiet rules. Einstein's curved space-time model doesn't just apply to Earth and the Sun. It works across every known scale, from small pebbles to supermassive black holes. This consistency is one of gravity's most striking features. No matter where you are in the universe, or how large or small the system, gravity follows the same rules. It doesn't do exceptions, unlike people. Start small. Even a speck of dust has mass, and therefore creates its own tiny dent in space-time. Of course, the effect is so faint it's completely drowned out by everything else around it, including the gravitational pull of your elbow. But in theory, it's there. Every bit of mass in the universe contributes to the overall curvature of space-time. No one gets a free pass. Zoom out a bit. Planets orbit stars, held in place by the geometry of curved space. Moons orbit planets in the same way. Spacecraft use these curvatures to their advantage, slingshotting around planets to gain speed. Not because the planet is giving them a push, but because they're moving through a curved path carved out by mass. It's celestial-level sat-nav, and it works with impressive accuracy. Then there are black holes, places where gravity becomes extreme. A black hole is formed when a massive star collapses under its own gravity, compressing into a region so dense that it warps space-time almost infinitely. Not even light can escape. The equations still hold, but the numbers start getting rather intense. It's like solving a parking dispute using quantum mechanics. Technically valid, but completely unnecessary for the task. At the largest scale, entire galaxies orbit around invisible centers of mass. We can't see all of it. In fact, most of the mass seems to be dark matter, which doesn't emit or reflect light. But we know it's there because of the gravitational effects. Galaxies spin faster than they should, given what we can see. So we measure the gravity, and it tells us there's something more. Something invisible pulling the strings. What ties all these examples together is the fact that gravity doesn't change its rules depending on size, temperature, or location. A falling apple, a planet in orbit, and a quasar 10 billion light-years away. All are shaped by the same principles. That's what makes gravity so quietly powerful. It's everywhere, always doing exactly what it's supposed to do, without ever making a fuss. This gives rise to a strange kind of comfort. A force so indifferent, so unchanging, that it helps shape the fate of stars and the tilt of your teacup, using exactly the same maths. This leads us to consider how gravity plays out not just across space, but also over time, and how its influence stretches from the beginning of the universe to far beyond our own lives. Gravity doesn't just act across space, it acts through time, not just the seconds ticking on a watch, but across billions of years, shaping the evolution of stars, galaxies, and entire cosmic structures. It's not in a hurry. Unlike humans, gravity has no deadline. It moves patiently, slowly shifting the shape of everything it touches over spans of time we can barely imagine. Let's begin with Earth. The pull of the moon on our oceans causes tides, but it also slows Earth's rotation very slightly. Over millions of years, days have become longer. When dinosaurs were about, a day was roughly 23 hours, which makes you wonder what their work-life balance was like. Probably still too many meetings. On longer timescales, gravity builds and destroys worlds. Clouds of gas collapse under their own gravity to form stars. Those stars live for millions or billions of years, burning through their fuel, swelling into giants, and eventually collapsing. Some explode as supernovae. Others shrink into white dwarfs, neutron stars, or black holes, all governed by the quiet but relentless pull of gravity. Galaxies, too, are shaped by gravitational attraction over vast spans of time. The Milky Way is slowly drawing in its smaller neighbors. In about 4 billion years, it will collide with the Andromeda Galaxy. The stars won't crash into each other. Space is mostly empty, but gravity will tear and reform both galaxies into something new. Slowly, silently, unbothered. Even space-time itself feels the pull. According to Einstein's theory, the presence of mass doesn't just bend space. It also affects the passage of time. Time runs slightly slower in stronger gravitational fields. That's not a poetic idea. It's measurable. Atomic clocks placed at different altitudes tick at different rates. If you live at sea level, you age a tiny bit more slowly than someone living up a mountain. The difference won't win you any prizes, but it's real. Then there's gravitational waves. Ripples in space-time caused by massive accelerating objects like merging black holes. These waves travel across the universe, passing through everything, compressing and stretching space ever so slightly. We only recently learned how to detect them. They don't change much for us here, but they're evidence that gravity isn't just static curvature. It can move, shift, and carry information through time. From the first stars to the death of the last black holes, gravity shapes the timeline of the universe. It guides the structure of everything, like a very quiet, very patient architect, with no intention of explaining itself. And it will keep working long after Earth, our sun, and whatever replaces smartphones have all disappeared. This leads us to consider the nature of that indifference. How gravity continues, unfazed, with or without anyone around to notice. Gravity has no opinions. It doesn't care who you are, where you live, or how urgently you want your toast to land butter side up. It simply does what it does. Continuously, quietly, everywhere. This may sound bleak, but there's something oddly comforting about a force so consistent and so completely uninterested in human affairs. A star doesn't burn brighter because someone's watching. A black hole doesn't pause to let a planet escape. Gravity affects all mass equally, without preference or prejudice. It shaped the early universe before there were eyes to observe it, and will continue long after those eyes have closed. If fairness existed in physics, gravity would be its patron saint. Except, saints don't usually tear stars apart. The forces that make our lives possible are entirely unbothered by us. Gravity pulls you to Earth with the same quiet strength it uses to bind galaxies together. If our planet vanished tomorrow, gravity wouldn't miss it. The moon's orbit would change, sure, the tides would stop, but the laws would carry on, unaffected. There's no grief in gravity, just mathematics. This indifference isn't cruel. It simply means gravity is reliable. We can build rockets, predict eclipses, and balance bridges, all because gravity follows the same rules every time. Unlike people, it doesn't make last-minute changes, forget birthdays, or, accidentally, eat the last biscuit. It's unemotional, but dependable. And, in a way, that makes gravity oddly peaceful. It isn't trying to impress anyone. It doesn't seek meaning or recognition. It just operates. Through space, through time, through everything. It gives form to galaxies, stability to planets, and the illusion of permanence to fleeting things like us. When we talk about gravity warping time or pulling light, it can sound dramatic. But the truth is, it's not doing it to be dramatic. It simply responds to mass and energy. The more of each you've got, the more space bends. There's no decision-making, no intention, just consequence. This understanding invites a different kind of appreciation. Not the kind that comes from being the center of attention, but from recognizing your place in a much larger system. One that has no idea you exist, but still follows laws that allow you to exist at all. This leads us to consider how this unfeeling force was slowly uncovered, not through sudden realizations, but through generations of careful observation and curiosity. Long before equations, telescopes, or theories about bent spacetime, people looked up and noticed something curious. Things moved. Stars wheeled overhead, the moon changed shape, and the sun returned every morning whether anyone asked it to or not. Patterns emerged, and with them, questions. Why do objects fall to the ground? Why do the heavens move so predictably? Early explanations, understandably, didn't involve gravitational constants or curved spacetime. They relied on what was visible and meaningful. In ancient Egypt, the sun's daily journey across the sky was the work of Ra. In Greece, Aristotle proposed that heavy objects naturally sought the center of the universe, which he believed was Earth. Not technically correct, but a decent first attempt considering they didn't have Google. People built structures aligned with the sky. Stonehenge, the pyramids, Mayan temples. These were not just architectural flexes. They were calendars, observatories, and spiritual centers. The movements of celestial bodies were recorded and studied long before we understood why they moved. Patterns were recognized, but the forces behind them remained a mystery. Meanwhile, on Earth, falling objects were just as puzzling. Drop a rock, it falls. Drop a feather, it flutters. Unless, of course, you're on the moon, in which case they fall together. But that distinction wouldn't be discovered for another few millennia. Early thinkers assumed heavier things fell faster. Again, wrong, but intuitively reasonable, like assuming teenagers enjoy getting up before 10 a.m. Despite the inaccuracies, these early observations were crucial. People were paying attention. They noticed regularity. The sun rises, seasons change, tides come and go, and they kept records. Babylonian astronomers charted planetary movements on clay tablets. Chinese scholars tracked solar eclipses. Indian and Islamic scientists refined models of celestial motion with impressive accuracy. The concept of attraction between objects wasn't yet part of the picture, but the groundwork was being laid. Careful measurement, pattern recognition, the realization that nature wasn't random, even if it was deeply confusing. These early observations weren't just myths or guesses. They were the first steps in a long and patient investigation. Eventually, these questions would evolve from why do things fall to what is the force that governs the motion of planets. But before we got to force, we needed to understand motion carefully, methodically, and with a willingness to be wrong more often than right. This leads us to consider the first major breakthroughs, the moments when gravity began to be understood not as myth or magic, but as something that could be measured, tested, and eventually explained. Eventually, people stopped just watching the sky and started trying to understand it. By the 16th and 17th centuries, a shift had begun. The universe was no longer seen as the realm of unpredictable gods or perfect crystal spheres. It was becoming a place that followed rules, and humans, remarkably, could figure those rules out. Slowly, with a lot of trial and error. One of the key figures in this early shift was Galileo Galilei. Instead of relying on logic or authority, he observed, experimented, and timed things. He rolled balls down inclined planes to study motion and discovered that objects accelerate as they fall. The longer they fall, the faster they go. Not the sort of thing that impresses your friends at a party, but extremely helpful for physics. Galileo also challenged the old belief that heavier objects fall faster than lighter ones. He showed that, when you remove the effect of air resistance, objects fall at the same rate regardless of mass. This sounds simple now, but at the time, it was a major correction, and it's still occasionally ignored by people who assume their phone will fall slower than their pint glass. It won't. Meanwhile, Johannes Kepler was studying planetary motion. Using detailed data collected by Tycho Brahe, he worked out that planets move in ellipses, not circles, around the sun. He identified 3 laws that described how planets speed up when they're closer to the sun, and slow down when farther away. He didn't know why this happened, but he showed how it happened, with remarkable precision. Then came Isaac Newton, who brought these ideas together. Building on the work of Galileo and Kepler, Newton formulated his law of universal gravitation. He realized that the same force pulling an apple to the ground could explain the moon's orbit around Earth, one set of rules governing both falling apples and celestial motion. An idea that had never been seriously proposed before. Newton didn't just offer an equation, he offered a new way of thinking, that nature followed universal laws, and those laws could be written in mathematics. Gravity wasn't just a property of Earth, it was a feature of the universe. That shift in perspective changed everything. Suddenly, people had a tool not just for describing motion, but for predicting it. It's worth remembering that these breakthroughs weren't flashes of divine genius. They were the result of careful measurement, slow thinking, and the willingness to question what seemed obvious. Galileo didn't time his rolling balls because he wanted to be controversial. He just thought the truth might be more interesting than the assumptions. This leads us to consider the tools and methods that allowed these insights to become more precise. The instruments and measurements that made gravity visible, predictable, and measurable across more than just our local patch of Earth. As our questions became more precise, our tools had to follow suit. Describing gravity with words and ideas was a start, but to measure it, to see what it's doing in numbers, we needed instruments. Careful ones, the kind that wouldn't be thrown off by wind, temperature, or someone sneezing too close to the table. One of the earliest clever tools was the pendulum. A simple swinging weight, it let scientists track time, motion, and acceleration. Galileo used them to study regular motion. Later, pendulums would be used to measure gravity in different locations. A surprising discovery, as gravity isn't exactly the same everywhere on Earth. It's slightly stronger over dense rock, and slightly weaker over deep oceans. Even gravity, it seems, has regional quirks. Then there was the torsion balance. In the late 18th century, Henry Cavendish used it to measure the gravitational attraction between lead spheres. It was the first time someone had weighed the Earth, so to speak. Cavendish wasn't trying to be dramatic. He was just investigating mass and distance. But his experiment let scientists calculate the gravitational constant, the key number in Newton's equation. With better clocks, telescopes, and measuring tools, astronomers could track the positions of stars and planets with increasing accuracy. They began to notice tiny anomalies. Mercury's odd orbit, for example, that didn't quite fit Newton's predictions. These weren't failures, they were clues. The instruments were revealing cracks in the old models, prompting newer, better explanations, which is essentially the scientific version of being told, your maths is off. Please try again. Fast forward to the 20th and 21st centuries, and gravity becomes measurable in ways Galileo could never have imagined. Satellite systems like GRACE gravity recovery and climate experiment can detect tiny changes in Earth's gravitational field, from melting ice sheets to underground water movement. By watching how gravity changes over time, we can monitor climate effects, tectonic activity, and even groundwater depletion. Not bad for something we used to measure with falling apples. LIGO. The Laser Interferometer Gravitational Wave Observatory takes this even further. It measures ripples in space-time caused by distant cosmic events like black hole collisions. It does this by detecting changes in length smaller than a proton's diameter, which, to put it in context, is the sort of precision most of us can only dream of when trying to cut wrapping paper in a straight line. Better tools haven't just confirmed old ideas. They've forced us to refine, revise, and sometimes throw out what we thought we knew. Instruments let us translate gravity from vague sensation into sharp data, revealing just how subtle and far-reaching this force really is. This leads us to consider what happens when we get it wrong, and how some of our most valuable lessons have come from being confidently, spectacularly incorrect. Science isn't a straight line, it's more like a long walk where you realize halfway through you've been heading in the wrong direction, and then act like you meant to go that way all along. Our understanding of gravity has been full of these wrong turns, mistaken beliefs that seemed entirely reasonable at the time but didn't hold up under scrutiny. Take Aristotle, for example. He thought heavier objects fell faster than lighter ones, and for centuries, people agreed. It seemed obvious. Drop a rock and a leaf, and the rock hits the ground first. Of course, air resistance wasn't factored in, mostly because air resistance wasn't really a thing anyone had defined yet. It took Galileo, and quite a bit of awkward experimentation, to point out that in a vacuum, everything falls at the same rate. Then there was the idea that the Earth stood still, while everything in the heavens revolved around it. The geocentric model was deeply entrenched, partly because it fit with how the sky appeared to move, and partly because people quite liked the idea of being at the center of things. It took Copernicus, Kepler, and finally Newton to show that actually Earth is just one planet orbiting the Sun, and the Sun isn't even particularly central in the grand scheme of things. Even Newton's work, revolutionary as it was, had its blind spots. His model of gravity as an invisible force acting instantly across space didn't quite add up when precision improved. The orbit of Mercury, for instance, didn't behave exactly as expected. It was close. Frustratingly close, but not perfect. For years, people thought there might be another hidden planet causing the wobble. They even named it Vulcan. Sadly, it never turned up. Einstein's general relativity eventually explained the orbit without needing any extra planets. Though Vulcan does still sound like a missed opportunity for sci-fi tourism. Sometimes, the mistake wasn't in the maths, but in how we interpreted it. For example, early astronomers couldn't detect Neptune because it was invisible. They found it because Uranus wasn't moving quite right. Using Newton's laws, they predicted where something must be. And there it was. The correction came not from saying, our theory is broken, but from saying, there must be something we haven't seen yet. And they were right. Science doesn't demand perfection. It just requires that we notice when things don't fit. Wrong ideas are part of the process. They show us where to look more closely, what to test again, and what assumptions might be quietly misleading us. Being wrong, usefully, is one of science's superpowers. This leads us to consider how we test these ideas, how experiments are designed not just to confirm beliefs, but to challenge them and reveal what the universe is really doing behind the curtain. If science were a story, the experiments would be the plot. They're where the questions meet the real world and where nature politely, or occasionally rudely, informs you whether your clever idea actually matches reality. With gravity, those experiments have ranged from rolling balls down ramps to catching ripples in space-time itself. At its core, a good experiment tests a clear idea. Galileo, for example, supposedly dropped balls from the Leaning Tower of Pisa to show that objects fall at the same rate, regardless of weight. Whether he actually did this is debated, but his inclined plane experiments were real and much easier to repeat without annoying the local council. Later, Newton's laws were tested through pendulum swings and astronomical predictions. You could work out where the moon would be next month, or how long it would take for a cannonball to hit the ground, assuming you could launch one without upsetting the neighbors. These tests weren't flashy, but they showed the maths matched reality well enough to build bridges and chart planets. One of the most precise early experiments was Cavendish's torsion balance, designed to measure the tiny gravitational pull between lead spheres. It didn't look impressive, just a wooden rod, some string, and weights in a sealed room. But it let scientists measure the gravitational constant g, a key number in Newton's formula. It also required a level of patience that would make modern researchers cry. Modern experiments have taken things to extremes. Drop towers allow researchers to study how things behave in freefall, often for a few seconds, which is about as long as funding committees stay excited. Parabolic flights, the ones astronauts train in, create short periods of microgravity, useful, but also a quick route to motion sickness and regretting lunch. Then there's LIGO, which detects gravitational waves using laser beams and mirrors spaced kilometers apart. It can sense distortions smaller than a proton's width, a level of precision so ridiculous it makes you question whether anyone involved ever gets to sleep. But it works, and it confirmed Einstein's century-old prediction that gravity can ripple through the universe. What all these experiments have in common is a careful isolation of variables. You can't test everything at once. You test one thing, hold the others steady, and watch for results, then repeat. Repeatedly. Until you're sure the effect isn't just a gust of wind or someone bumping the table. This leads us to consider how these discoveries weren't made by individuals working in isolation, but by communities of scientists, each building carefully, and sometimes awkwardly, on the work of others. The story of gravity isn't one person having a clever thought under a tree and calling it a day. It's a slow, communal effort, a scientific relay race stretching across cultures and centuries, with each generation passing the baton slightly further than the last. Gravity, like most good ideas, took a village, a very patient one. After Newton, the work didn't stop. It spread. Mathematicians in France refined his equations. Astronomers in Germany tracked more precise planetary data. Observatories were built around the world to map the stars, predict eclipses, and test theories. The process was messy, but productive. Scientific understanding doesn't progress in neat chapters. It lurches forward, doubles back, and occasionally loses its shoes. International collaboration wasn't always easy. Politics, language, and geography made it awkward. But gravity didn't respect borders, so eventually, neither did science. A good example is the measurement of Earth's shape. Scientists from different countries worked together, sending expeditions to the equator and the poles to measure how gravity changes with latitude. Earth isn't a perfect sphere, it's slightly squashed, like a rugby ball someone sat on. Over time, national observatories became international missions. Telescopes were shared, satellites launched, and data made public. Einstein's theories were tested using observations from teams all over the world. When LIGO detected gravitational waves in 2015, it wasn't one lab. It was the result of decades of collaboration across institutions, countries, and time zones. And probably a fair number of stressed out postgraduates. Even disagreement played a role. Competing theories forced better experiments. Contradictions sparked conversation. One scientist's error became another's breakthrough. This wasn't teamwork in the sentimental sense. It was more like group editing. One person writes a draft, another says it's wrong, a third tries something else, and eventually someone stumbles across something that works. Then everyone argues about who gets their name on it. Modern physics depends on this shared structure: peer review, open data, global conferences, all designed to spread knowledge, challenge assumptions, and build on one another's work. You can't test a theory on black hole collisions unless someone else builds a detector. And you can't build a detector without teams of engineers, physicists, and the occasional accountant asking if you really need another 40 million mirror. This approach, slow, collective, sometimes frustrating, is how science gets stronger. It stops us from getting too attached to our own ideas and forces each discovery to stand up to challenge. Gravity became one of the best understood forces, not because of genius alone, but because people kept checking each other's work for 400 years. This leads us to consider where we stand now. How modern tools and collaboration have brought gravity into sharper focus than ever, and yet still left us with questions. Thanks to centuries of methodical work, gravity has gone from a vague curiosity to one of the most precisely measured forces in science. We can now detect its effects down to absurdly tiny scales. Whether it's a falling apple or the wobble of a distant star, the tools are sharper, the models more refined, and the questions, somehow, even more difficult. Take GPS, for example. The system depends not only on accurate positioning, but also on accounting for gravitational time dilation, a prediction of Einstein's relativity. Satellites orbiting above Earth experience slightly weaker gravity than we do on the surface, so time ticks fractionally faster for them. If this wasn't corrected, your navigation would be off by kilometers each day. So next time it correctly tells you to turn left at the roundabout, you can thank general relativity. Then there's the Gravity Probe B experiment, launched by NASA to test two key predictions of Einstein's theory: frame dragging and geodetic precession. These are effects that occur when massive, rotating bodies, like Earth warp space-time in complex ways. The probe used ultra-precise gyroscopes, the kind of equipment that makes "don't bump the table" take on a whole new meaning, and confirm the predictions to remarkable accuracy. We've also got the LIGO and Virgo observatories, which measure gravitational waves from events billions of light-years away. These waves, rippling through the fabric of space-time, are detected as shifts in laser paths, measured to a fraction of a proton's width. This is the physics equivalent of noticing your neighbor's cat sneezing by watching the curtains flutter in your attic. Meanwhile, satellites like GRACE measure how Earth's gravity changes over time. These shifts can reveal everything from groundwater loss to melting glaciers. In a sense, gravity has become a tool not just for studying the cosmos, but for monitoring our own planet. The quiet tug of mass can show us changes we might otherwise miss. Even laboratory experiments have reached astonishing precision. Physicists now test the limits of Newtonian gravity at sub-millimeter scales, looking for signs of new forces or deviations. So far, Newton's laws still hold, but scientists keep checking, just in case the universe is hiding something awkwardly inconvenient in the decimal places. Despite all this progress, gravity still refuses to reveal its most basic nature. We can describe how it works to extraordinary accuracy, but we still don't fully know why it works that way. It's like having a watch that always tells the right time, but no one can quite agree on what's ticking inside. This leads us to consider the mystery that still surrounds gravity, and why, after all this time, it remains one of the most puzzling aspects of the universe. After all the effort, the equations, the satellites, the laser beams bouncing down vacuum tubes, one awkward truth remains: gravity is still weird. We understand how it behaves. We've mapped it, modeled it, measured it to ridiculous precision. But when it comes to explaining what it actually is, the universe just stares blankly and changes the subject. The biggest issue is that gravity doesn't fit neatly with the other forces. Electromagnetism and the strong and weak nuclear forces are all described by quantum field theory, the mathematical framework that's been tested to absurd degrees of accuracy. Gravity, on the other hand, is still described by general relativity, a classical theory, not a quantum one. It's like trying to run the latest software on a typewriter. Attempts to build a quantum theory of gravity have led to exotic ideas: string theory, loop quantum gravity, holographic principles. These theories aim to explain gravity using the language of quantum mechanics. But so far, none of them have produced testable predictions. It's all rather elegant, but unfortunately, you can't measure elegance with a telescope. Then there's the graviton, the hypothetical particle that, in theory, would carry the force of gravity. We've never detected one. If it exists, it would be so weakly interacting that it's essentially impossible to spot with current technology, which makes it a bit like trying to confirm the existence of ghosts by checking if they've paid council tax. Gravity also refuses to behave at cosmic scales. Galaxies rotate in ways that don't make sense unless there's a lot more mass than we can see. To explain this, scientists propose dark matter, invisible stuff that only interacts through gravity. It's either a real thing we've yet to detect, or gravity itself needs a rewrite at large scales. Either way, not ideal. At the other end of the spectrum, near black holes, gravity becomes completely uncooperative. The equations of general relativity predict singularities, points of infinite density and zero volume, where the laws of physics break down. Not just we don't know what happens, but the maths literally explodes. Always reassuring. So, we're left with a force that's essential to everything, from falling apples to the birth of stars, but which remains fundamentally mysterious. It shapes the universe, yet refuses to explain itself properly. Like a teacher who marks your paper with "see me," but never says what's wrong. This leads us to consider the possibilities ahead. What might lie beyond our current understanding, and how new discoveries could finally bring gravity in from the cold. If gravity is still a mystery, then the future of gravitational research looks like a mixture of serious physics and the scientific equivalent of rummaging behind the sofa for lost clues. There are many promising ideas, but none have quite cracked it. What's clear is that gravity will continue to be where the weirdest conversations in physics tend to happen. One major direction is quantum gravity. The search for a theory that unites gravity with quantum mechanics. String theory is a popular candidate. It suggests that particles are actually tiny vibrating strings, and gravity arises naturally within its framework. Unfortunately, it also predicts a whole lot of extra dimensions and particles that we've never observed, which makes it feel a bit like science fiction that accidentally got a PhD. Then there's loop quantum gravity. Instead of strings, it suggests that space-time itself is made up of tiny loops. These loops form a kind of woven fabric, not metaphorically, but literally in a mathematical sense. If true, it would mean space-time isn't smooth, but grainy, like cosmic couscous. The problem is, we've got no experimental spoon to test the texture. Some physicists think we need to go back even further and rethink our assumptions. Maybe gravity doesn't need to be a force at all. Some newer theories suggest it might be an emergent property, something that arises from more fundamental bits of information, which is quite a thought. The thing that holds stars and planets together might be a side effect of maths trying to tidy itself up. Gravitational waves are also offering new ways in. Observatories like LIGO and Virgo are listening for ripples in space-time from the most violent events in the universe. As sensitivity improves, we might spot things we've never seen before. Black hole mergers, neutron star quakes, maybe even echoes of the Big Bang. It's like turning up the volume on a universe that's been humming in the background this whole time. On a more speculative front, there's the idea of testing gravity in space with future missions. Ultra-sensitive detectors aboard satellites could look for tiny shifts that might hint at new physics. Some even want to build instruments in deep space, away from Earth's noise. All very clever, assuming we can get anything launched on time and without the usual budget drama. Meanwhile, data from telescopes and particle accelerators might help by ruling out some of the more outlandish theories. Even when experiments don't find what we hope for, they can still tell us what's not going on, which is surprisingly helpful when you're trying to pin down something as elusive as gravity. All of this means we're in a strange position. We've never understood gravity more precisely, and never felt further from truly understanding it. This leads us to consider the biggest question of all: why gravity exists at all, and what its origin can tell us about the nature of reality. Of all the questions in physics, why is there gravity? Might seem the most obvious, but it's also one of the hardest to answer. It's like asking why there's up, or why cheese melts. We can describe what happens, even model it in exquisite detail. But the reason behind gravity's existence? That remains awkwardly unanswered. At its core, gravity is the tendency of things with mass to attract each other. But why should mass do that? In general relativity, the answer is, it doesn't. Not directly, anyway. Instead, mass and energy curve space-time, and that curvature affects how objects move. Like placing a bowling ball on a trampoline and watching marbles roll towards it. Except the trampoline is four-dimensional. And also, nothing like a trampoline. But general relativity doesn't explain why mass curves space-time. It simply assumes that it does. It's a bit like a game where the rules are never explained. You're just expected to play along and not ask too many questions. And when scientists do ask those questions, they tend to vanish into rabbit holes full of maths and metaphysics. Some theories suggest that gravity could be the result of something deeper. An emergent phenomenon, not fundamental at all. It could arise from the collective behavior of microscopic things we haven't discovered yet. In that case, gravity wouldn't be a basic feature of the universe, but more like steam rising from a kettle, a consequence, not a cause. Others propose that gravity might be linked to the flow of information, that the way information is distributed in the universe somehow gives rise to what we call gravitational effects. If that sounds more like philosophy than physics, you're not wrong. But oddly enough, this line of thinking has led to some useful ideas about black holes and the limits of knowledge. Another oddity: gravity is by far the weakest of the four known forces. A fridge magnet can easily overpower the entire gravitational pull of the Earth. Why gravity is so weak, and yet dominates the large-scale structure of the universe, is one of those annoying contradictions that keeps physicists up at night, presumably next to their fridge magnets. Even asking why gravity exists may turn out to be the wrong kind of question. It might be like asking why 2 plus 2 equals 4, not because someone made it so, but because that's just how logic unfolds in the kind of universe we happen to live in. Unhelpful, perhaps, but strangely consistent. This leads us to consider gravity's role in the grand scheme. Not just as a feature of our universe, but as something that may vary, disappear, or take strange forms in universes beyond our own. If gravity feels strange here, imagine what it might be like somewhere else. Assuming there is a somewhere else. The idea that our universe might be just one of many, each with its own version of physics, has gone from science fiction to something physicists now discuss with a mostly straight face. This brings us to the concept of the multiverse. Not the superhero kind, unfortunately, but the theoretical possibility that our universe is part of a much larger system. Some versions suggest there could be countless universes, each with different laws, constants, and initial conditions. In some, gravity might be stronger or weaker. In others, it might not exist at all. One reason this idea is taken seriously is inflation theory. The idea that the early universe expanded rapidly in a burst of exponential growth. Some models suggest this inflation could happen repeatedly, like bubbles forming in a fizzy drink. Each bubble becomes its own universe, with its own properties. Our universe, then, would be one bubble in a possibly infinite foam. In these other hypothetical universes, the strength of gravity could vary drastically. Too strong, and matter might collapse before galaxies can form. Too weak, and everything just drifts apart. No stars, no planets, no chemistry. It's not that gravity was designed to be just right here, it's that we wouldn't be around in a universe where it wasn't. This is the anthropic principle. Not especially satisfying, but annoyingly hard to argue with. String theory adds its own twist. If the theory is right, then there could be a huge number of different ways to set up a universe, each corresponding to a different version of compactified dimensions. The number is large, something like 10,500 possible universes. That's not a typo. That's a number so ridiculous it makes the lottery look like a fair fight. Some researchers have tried to test aspects of the multiverse idea, but direct evidence is tricky. Other universes wouldn't necessarily interact with ours, and if they did, the effects might be indistinguishable from noise or coincidence. It's the cosmic equivalent of living in a locked house and trying to work out what your neighbors are doing by listening through the plumbing. Still, thinking about other universes helps sharpen our understanding of this one. It reminds us that the laws of physics, which seem fixed and inevitable, might just be one possibility among many. Gravity, then, might not be a universal truth, just the version of reality that happened to come out of our particular cosmic draw. This leads us to one final question. Not just how gravity works, but what it reveals about the nature of space-time itself, and whether there's something even deeper shaping the universe behind the scenes. After all this talk of curves, warps, and invisible forces holding the universe together, we're left with a rather unsettling possibility. Gravity might be telling us something we've missed entirely about reality. Something deeper than force fields and falling apples. Something about the nature of space, time, and perhaps even what real means. Let's start with the obvious. Space-time isn't just a backdrop, it's part of the machinery. In Einstein's general relativity, gravity is what happens when mass changes the geometry of this space-time fabric. But that fabric isn't made of anything. It's not a substance. It's the structure of existence itself. Which is a rather fancy way of saying, nobody has a clue what it really is. This oddness has led some physicists to ask whether space and time are actually fundamental at all. Maybe they emerge from something else, some underlying quantum process. Some have proposed that the building blocks of reality might be abstract things, like information, or mathematical relations, or networks of interacting events. Yes, it's abstract. No, it doesn't come with a helpful diagram. In these models, gravity isn't a force that travels across space. It's a large-scale illusion created by deeper processes playing out in microscopic or even dimensionless ways. One idea, called entropic gravity, suggests gravity might be a kind of statistical effect. The universe trying to maximize disorder. Which is ironic, really, considering how tidy gravity makes things look. This turns gravity from a straightforward pull into a signpost, a clue pointing towards whatever reality is really made of. It also connects with black holes in a surprising way. Some researchers argue that the information stored on the surface of a black hole, rather than inside it, hints at space itself being holographic. As in, the 3 dimensions we experience may be projected from something simpler and flatter. Just don't expect gravity to help with the projector alignment. Even time might be an emergent property. Some quantum gravity theories suggest that what we experience as the flow of time could arise from correlations between quantum states. If that sounds confusing, well, it is. Time turning out not to be real might be the most difficult bit of physics to explain to your nan, or your cat, or yourself, really. So, gravity may not be just a force, or even just geometry. It may be a manifestation, a side effect, of something deeper we haven't yet named. In trying to understand gravity, we may be trying to understand the source code of the universe. Whether we're clever enough to read it is still up for debate. This leads us, finally, to pause. After all these questions and models, what do we really know about gravity, and what remains in the dark? So, after nearly 14 billion years of gravity doing its thing, and a few centuries of us watching it rather intently, where does that leave us? The answer, unsurprisingly, is somewhere between not bad and still scratching our heads. We've made real progress. But there are still big, glaring gaps. Gravity is both familiar and mysterious. Like an uncle who shows up to every family gathering but never explains what he does for a living. Let's start with what we do know. We know gravity pulls. We know it shapes planets, stars, galaxies, and the entire universe. We understand how it behaves in most situations, well enough to land rovers on Mars, track black holes colliding, and model the shape of the early universe. Newton's equations still work for everyday things. Einstein's theory of general relativity takes over when space-time curves significantly. We've confirmed key predictions of general relativity. Light bends around massive objects. Time ticks more slowly near strong gravitational fields. Gravitational waves exist. We've detected them from distant black holes smashing into each other. All of this fits the theory rather well, like a slightly smug jigsaw puzzle. But then things get awkward. General relativity breaks down at tiny scales, near the centers of black holes or at the Big Bang. That's where quantum theory takes over. Trouble is, Quantum mechanics and general relativity don't get along. It's not so much that they disagree, it's more that they speak completely different languages and refuse to get a translator. We also don't know what causes gravity at the quantum level. Is there a graviton particle? Maybe. Is gravity emergent from something more fundamental? Possibly. Are we even asking the right questions? Who knows? There are theories. String theory, loop quantum gravity, others with longer names. But no firm answers yet. It's like trying to guess the plot of a novel by reading the first and last pages, and realizing they may not be from the same book. Dark matter is another blind spot. We can see its gravitational effects, galaxies spinning faster than they should, but we can't detect it directly. Dark energy, even worse, appears to make up most of the universe and is driving it apart. We've named it. That's about it. Calling it dark is honest at least. Still, uncertainty isn't failure. It's a sign of a live question, the best kind in science. Gravity has taken us from apples falling in orchards to black holes colliding across the cosmos. It connects the very small to the very large, even if the connection is currently held together with metaphysical duct tape. This leads us to a kind of cosmic humility. The more we learn about gravity, the more it reveals how much we still don't understand about the universe and perhaps about our place in it. Tonight, we end not with a grand conclusion, but with a gentle shrug. Gravity, the thing that keeps your feet on the ground and holds galaxies together, is still in many ways an unsolved riddle. We know how it behaves. We can measure it, predict it, even use it to steer spacecraft. But why it exists at all, that remains oddly out of reach. And yet, for something so fundamental, gravity is quietly patient. It works everywhere, all the time, without needing our understanding or permission. It doesn't flash or spark or shout. It's just there. You don't get explosions or rays or weird particles flying around, just falling apples, orbiting moons, and the occasional collapsing star. Bit of a minimalist, really. In some ways, our ignorance is useful. It tells us where the edge of knowledge is, where our best theories begin to wobble. That edge is where new ideas start, the sort that might one day explain why black holes evaporate, or whether gravity really has a quantum side hiding somewhere beneath the surface. For now, we live in a universe shaped by gravity, from the curve of Earth's horizon to the structure of cosmic filaments stretching across billions of light years. It carves the paths of planets, sets the rhythm of orbits, and quietly governs the geometry of space and the flow of time itself. And on a human scale, it's the reason we grow upright, drop toast butter side down, and get sore knees when we crouch for too long. Gravity is not just out there in the cosmos. It's here, stitched into every moment of our daily lives, even when we forget it's doing anything at all. Of all the forces in nature, gravity is the one most tied to our sense of place. It reminds us that we are not floating, but anchored, held by the mass of our world, which itself is held in motion by the sun, which in turn orbits something larger still. Gravity links us to the cosmos, not through imagination, but through fact. So we end where we began, grounded, quite literally, one force, pulling gently on everything, everywhere, all the time, steady, quiet, mysterious, and frankly, still not answering any of our follow-up questions. Typical. And with that, we leave gravity alone for a while, still falling, still pulling, whether we understand it or not. If gravity leaves us with questions, it also leaves us with direction, quite literally. Things fall down, planets orbit forward, and scientists press on, usually uphill. From Newton's falling apple to LIGO's whisper from a black hole merger, each step has opened a slightly wider door into how the universe works. But now, some of those doors seem firmly shut, and a crowbar may be required. A key target is quantum gravity. We have excellent theories for big things, general relativity, and for tiny things, quantum mechanics. Sadly, they don't get on. Like two distant cousins forced to share a bunk bed, the combination is awkward. We don't yet have a working theory that explains gravity at both the cosmic and subatomic levels. String theory and loop quantum gravity are among the contenders. But at the moment, they're all theory, no test. At the same time, physicists continue to probe the limits of general relativity. Einstein's equations have passed every test so far, from GPS satellites to the bending of starlight during solar eclipses. But in extreme places, like inside black holes or just after the Big Bang, we expect things to break down, which, to be fair, seems understandable. Those environments aren't exactly built for stability. Then there's dark energy. It acts a bit like gravity's moody sibling, not pulling things together, but pushing them apart. Whatever it is, it's causing the expansion of the universe to speed up, which is rather inconvenient if your job is explaining how things are supposed to slow down under gravity's influence. What dark energy actually is remains unclear. Best guess, something we made up to patch a hole in the maths. Not that we're bitter. In the lab, research continues on gravity at small scales. How weak is it, really? Can we detect quantum effects in gravity? And does gravity behave differently over huge distances? These are questions physicists are actively trying to answer. With torsion balances, atom interferometers, and quite a few grant applications that use the word fundamental at least 5 times. Space offers opportunities too. Missions like LISA Laser Interferometer Space Antenna aim to study gravitational waves from space, looking deeper into the history of the universe than ever before. Meanwhile, telescopes scan the sky for signs of black hole collisions, gravitational lensing, and subtle warps in the cosmic microwave background. Gravity, it seems, leaves fingerprints everywhere. Some even ask whether gravity is emergent. Not a fundamental force at all, but something that arises from deeper physical laws. It's a controversial idea, like suggesting water isn't wet. It just acts that way when you get enough molecules together. But if it turns out to be true, it could revolutionize physics. Again, which is annoying, considering how long it took us to get this far. This leads us to consider something even more baffling: the idea that space and time themselves may not be as solid as they seem. What if gravity is just a symptom of how the universe encodes information? That, I'm afraid, is tomorrow's headache. Let's bring it back to where you are right now. Hopefully upright, possibly slouched, and definitely under the influence of gravity. This force, which we've chased from Newton to black holes, is also the reason you can drop your phone and then regret it. Gravity may be mysterious on the cosmic scale, but on human scales, it's deeply personal. It starts early. As a fetus, gravity helps orient your developing body. After birth, it shapes how your bones grow, how strong your muscles become, and even how your balance system in the inner ear works. Remove it, say, in space, and your body quickly starts to fall apart. Bones weaken, fluids shift, and muscles atrophy. It turns out your skeleton was hoping you'd stay on Earth. And speaking of Earth, gravity is what keeps our atmosphere wrapped neatly around the planet. Without it, we'd lose our breathable air to space in fairly short order. Not to mention oceans, weather, and the ability to make decent tea. You may not think about it every day, but gravity is what makes this planet habitable. Not warm, not sunny, just anchored. It also defines how we move. The amount of force you need to walk, jump, or carry shopping bags is set by Earth's gravitational pull. It's why lifting a suitcase feels harder here than it would on the moon. Though there, you'd struggle to pack shampoo properly, so swings and roundabouts. Gravity affects your sense of time too, although not in ways you'd notice day to day. Thanks to general relativity, clocks tick slightly slower in stronger gravity. So, technically, your feet age more slowly than your head, not by much, unless you're an astronaut circling Earth, but enough that the GPS satellites need to account for it. Otherwise, your satnav would think you were somewhere in the next village over. Psychologically, gravity also gives us a sense of place. Up and down only make sense because of it. Without gravity, orientation becomes arbitrary. Which is probably why astronauts occasionally report feeling upside down when floating in microgravity, even when they're not. It turns out our brains are quietly obsessed with knowing which way is down. And of course, gravity will eventually have the last word. As we age, gravity plays a steady role in wear and tear, from joint strain to compression of the spine. If you've ever ended the day slightly shorter than you started it, that's gravity too. It's not malicious, just persistent. So the next time you drop something, trip over nothing, or find your tea settling just so, you're interacting with one of the four fundamental forces of nature. The quiet one. The one that never takes a break. Always pulling, always present. And apparently, not keen on letting go. Despite centuries of careful observation, experimentation, and the occasional Apple-related anecdote, gravity remains stubbornly mysterious. We can model it, we can predict it, but we still don't really know what it is. This is one of those scientific situations where the universe is playing a long-running joke, and we're not entirely sure if we're in on it. The biggest unresolved question is whether gravity has a quantum nature. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, all play nicely with quantum theory. Gravity, however, refuses to fit in. It's like trying to shove a cat into a shoebox, technically possible, but no one's walking away without scratches. Einstein's general relativity describes gravity beautifully at large scales. It tells us how planets orbit, how black holes form, and how light bends around massive objects. But zoom in to the tiniest scales, particles and atoms, and relativity starts to fall apart. There's no confirmed quantum theory of gravity, no graviton particle we can detect, and no consensus on how space and time behave near singularities. String theory has tried to fill that gap, offering a model where gravity naturally emerges from tiny vibrating strings. But so far, there's no experimental evidence that these strings exist. Other attempts, like loop quantum gravity, try to break space-time into discrete chunks, sort of like cosmic Lego. Also interesting, also unproven. Then there's the puzzle of dark matter and dark energy. Galaxies spin faster than they should, as if there's extra invisible mass holding them together. Dark matter, and the expansion of the universe is speeding up, as if something, dark energy, is pushing space apart. Both of these might hint at deeper truths about gravity. Or They might point to entirely new physics. Either way, it's all rather vague. Imagine trying to solve a jigsaw puzzle with half the pieces still in the box, and the picture on the lid keeps changing. Another unsolved mystery. Why is gravity so weak? Compared to the other forces, gravity is astonishingly feeble. A fridge magnet can overcome the gravitational pull of the entire Earth. This discrepancy has led some physicists to propose extra dimensions, the idea that gravity may be leaking into other realms we can't observe. Again, a fascinating theory. Again, not yet confirmed. There's also the issue of time. General relativity treats time as part of the fabric of space, something that bends, stretches, and slows down near mass. But in quantum mechanics, time just ticks along in the background like an indifferent referee. Reconciling these two views may require rethinking what time even is. Not ideal when most people still struggle with daylight saving. So gravity continues to work. Reliably, measurably, every day. But without revealing its full story. We understand how it behaves, but not why it behaves that way. Which, to be fair, also applies to most cats and teenagers. This leads us to consider one last idea. Perhaps we don't just need new data or new equations, but an entirely new perspective. So where does this leave us? Gravity, the force that began as a falling apple and ended in warped space-time, has taken us on a rather peculiar tour of the universe and ourselves. Along the way, we've watched stars collapse, clocks slow, and moons stay loyally in orbit, all thanks to one quiet, unrelenting pull. Let's start with what we're confident about. Gravity is a force of attraction between masses. It acts over long distances and always pulls, never pushes. It's responsible for the structure of the cosmos, from the shape of planets to the formation of galaxies. It even dictates the large-scale fate of the universe. Not bad for something that doesn't make much noise. Einstein's theory of general relativity remains our most accurate model for how gravity behaves, particularly at large scales. It treats gravity not as a force, but as the effect of mass-bending spacetime. This idea has passed every experimental test thrown at it, from the orbit of Mercury to the bending of light during eclipses, to the detection of gravitational waves. At human scale, gravity keeps us grounded, governs how we move, and quietly erodes our posture over time. It affects time, biology, engineering, and even how we feel about up and down. Most of us don't think about it much until we drop our phone or climb the stairs with slightly more optimism than we should have. And yet, gravity also marks the boundary of our ignorance. We don't know how it fits with quantum mechanics. We haven't detected the graviton. We don't fully understand what happens inside a black hole. And we've no idea why the universe is accelerating, or whether gravity itself might one day need revising to explain it. Some theories try to bridge the gap. String theory, quantum loop gravity, emergent gravity, but none have won the day. In fact, we might still be looking at the whole thing from the wrong angle. As with most difficult problems, there's always the unsettling possibility that we haven't even asked the right question yet. What's clear is that gravity sits at the heart of both the most familiar experiences, like walking and falling, and the most extreme environments, like neutron stars and black holes. It's both everyday and exotic. And that contrast may be why it's been so hard to fully pin down. Bit like trying to understand a cat that can also warp time. So tonight, gravity remains what it's always been: essential, invisible, and strangely elusive. We've mapped its effects across the cosmos and within our own bones, but its true nature, still pending, still pulling, still not quite letting us go. By now, it should be clear that gravity isn't just something that keeps your feet on the ground. It's the quiet architect behind the scenes. From galaxy clusters to your spine, it has a say in nearly everything with mass. Which is, frankly, rather a lot of things. Even your own body plays a role in shaping gravity. Yes, yours. Every mass, no matter how small, bends space. Technically, you do too. If we had sensitive enough instruments, we could detect the tiniest warp around your body. It's just that Earth, weighing in at 6 billion trillion tons, is doing the same thing, but more noticeably. Your contribution is, let's say, politely ignored. Still, the principle is sound. You are participating in the gravitational structure of the universe simply by existing. Your atoms, drawn together by fundamental forces, now huddle in your current form, exerting a gravitational pull on everything else. You're gravitationally tied to the planet, the moon, and, in an absurdly small way, the rest of the cosmos. This makes gravity feel rather more personal. It's not just something acting on you, you are also a source of it. In fact, every decision you make, from where you sit to where you walk, slightly changes how your mass affects spacetime. You're warping the geometry of the universe just by reaching for the kettle. It's not useful warp, mind you, but still. And you, like everything else, fall under gravity's influence. You fall when you trip, yes, but you also fall around the sun. The Earth's orbit is a continual fall, it just misses. The moon's doing the same with us. You're on a world that's forever dropping through curved space. The fact we call this stable says a lot about how normal we find weird things. Now zoom out. You are part of a species that's just begun to grasp this force properly. We've dropped probes on comets, measured black holes colliding 1 billion light-years away, and built theories that predict time slowing and light bending. Not bad, considering we only stopped thinking Earth was the center of the universe about 5 minutes ago. And gravity is still shaping our future. It limits how we leave Earth. It controls how we build satellites. It's one of the biggest engineering challenges for living on other planets. And it's not going away. Not until the last stars flicker out, the galaxies drift apart, and whatever remains is left to cool and stretch across the fabric of space. So tonight, remember this. Gravity is not just something that acts upon you. It is something you belong to. You are not separate from the universe's architecture. You are stitched into it. Slightly curved, occasionally clumsy, but firmly held. We end, appropriately, where everything else began, with a fall. Newton's apple, the Earth orbiting the Sun, a distant galaxy being pulled into a cluster. Gravity governs all of it. And yet, for all we've uncovered, we're still only partway through the story. The next chapters, whatever they are, will hinge on questions we've barely managed to ask. The biggest one is this: how does gravity fit with quantum mechanics? Right now, we've got two towering pillars of physics. General relativity works beautifully for stars, planets, and black holes. Quantum theory explains atoms, particles, and fields. But put the two together, say, inside a black hole, and things get awkward. Like trying to fit a tractor engine inside a smartwatch. Several theories aim to reconcile this. String theory suggests that particles are tiny vibrating loops. Loop quantum gravity imagines space-time itself is made of discrete chunks. Others think gravity might be emergent, not fundamental. More like temperature than electricity. Which, if true, would make gravity a very convincing illusion. Like most meetings that could have been an email, there's also the mystery of dark energy. Observations show the universe's expansion is speeding up, not slowing down. Gravity should be pulling everything back. So either something else is pushing, or gravity behaves differently on huge scales. It's like spotting a leak in your roof, only to find out the entire house is expanding. Then there's dark matter, which doesn't emit light or interact with anything, except gravitationally. We've never seen it directly, but it's holding galaxies together. Is it a particle? A field? A quirk in how gravity behaves at galactic scales? Until we know, it remains the universe's least helpful flatmate, always around, never visible, refuses to explain itself. New telescopes and gravitational wave detectors might help. We're now watching the universe in more ways than ever, listening to it really. Each merger of black holes, each flicker of starlight bent by distant mass, brings a new data point. Gravity, it seems, never stops talking. We just needed better ears. In labs on Earth, physicists are probing gravity at tiny scales, looking for deviations, quantum effects, or signs of hidden dimensions. So far, gravity is being stubbornly well behaved, which is either comforting or infuriating, depending on how much grant money you've spent. So what falls next? Possibly our current understanding, possibly nothing, and general relativity carries on serenely for another 100 years. Or perhaps someone will stumble across a clue that finally cracks it all open. Not unlike Newton watching that apple drop and realizing it was never just about the apple. Tonight, gravity remains the universe's most familiar mystery, constant, quiet, oddly personal, and still pulling us toward the unknown. We began with a fall. We end in orbit. It's a tidy loop. Quite fitting, considering gravity loves a good circle. After all the space-time stretching, planetary spinning, and black hole collapsing, we're still dealing with the same quiet force that's kept our feet on the ground and our moon in the sky. Gravity hasn't changed. But maybe we have. Over the past journey, we've seen gravity shape everything from the trajectory of tennis balls to the fate of galaxies. We've watched it slow time, bend light, and hold clusters of stars together for billions of years. And we've learned it's not just a force pulling things down. It's a curvature of space-time, a clock tweaker, a structure former, and, occasionally, an ankle breaker. We've also realized that gravity has limits. Or, at least, our understanding of it does. It stops short at the quantum world, stumbles at the edge of black holes, and throws up its metaphorical hands when asked about dark matter or dark energy. Which is surprisingly relatable, really. Sometimes, even the universe doesn't have the answers. Still, gravity has been a reliable guide. It's let us map the solar system, land probes on comets, and predict eclipses centuries in advance. And though we might not know where every gravitational wave comes from, we can at least detect them. Ripples in reality, faint whispers from distant catastrophes. On Earth, it remains part of daily life. It shapes rivers, governs weather, and subtly ruins your back after age 30. Despite its cosmic reach, gravity never forgets to pull your cup off the kitchen counter at the worst possible moment. A humble reminder that even universal forces have a sense of timing. There's something oddly comforting about gravity's consistency. Stars explode, economies wobble, but gravity? Still plugging away, 9.8 meters per second squared. It's the one law that never gets repealed, renegotiated, or rebranded. Which, in today's climate, is frankly heroic. As we leave gravity behind, at least in discussion, we step into a larger landscape, because everything else in the universe must reckon with gravity. But it must also work with light, heat, pressure, quantum behavior, chemistry, and life. Gravity's grip may be long, but it doesn't work alone. This leads us to consider what happens when matter begins to organize, when forces interact, and when gravity becomes just one actor in a much messier story. From here, we move from what falls to what forms. Gravity alone doesn't build a world. It pulls, certainly, shapes trajectories, forms orbits. But without pressure, temperature, or collisions, you just have everything falling forever. To get structure, you need resistance, you need balance. And that's where other forces step in. Not to oppose gravity, exactly, but to complicate things in helpful ways. Let's start with pressure. When gravity tries to squash gas into a denser clump, pressure pushes back. This counterforce can hold clouds of hydrogen in a sort of limbo, neither collapsing into stars nor drifting apart. But as the cloud cools, pressure drops. Eventually, gravity gains the upper hand, and things start falling inward. Not in a dramatic rush, more a slow, inevitable crumpling. As matter compresses, it heats up. Collisions between particles transfer energy, raising the temperature. At a certain point, atoms start moving so quickly and densely that fusion begins. The process that powers stars. So gravity creates the conditions, but it's nuclear forces that do the real heavy lifting. Or, in this case, the heavy fusing. The balance between gravity and pressure defines what forms. Too much mass, and gravity wins. You get a black hole. Too little, and the object can't sustain fusion. You get a brown dwarf. Just the right balance, and you get a stable star. It's like the universe is running a very long, slow bake-off, with gravity as the overconfident judge who occasionally swallows the contestants. But forming a star is only part of the story. Around new stars, disks of gas and dust can flatten and clump together into planets. Again, gravity gathers things, but other forces shape what happens next. Chemical bonds, radiation pressure, angular momentum. It's less like a clean blueprint, more like throwing ingredients in a bowl and seeing if anything edible survives. Over time, these processes build complexity. You get moons, rings, atmospheres. Rocks crash together, melt, and cool. Some planets end up with thick atmospheres. Others lose theirs to solar winds. Some form magnetic fields, others don't. Gravity sets the stage, but what develops on it depends on many smaller forces bickering behind the curtain. Eventually, this interplay gives us planets like Earth, solid ground, liquid water, breathable air. None of it is inevitable. All of it rests on narrow balances between gravity, chemistry, and heat. And none of it would be here if gravity hadn't pulled the first atoms together, then backed off just enough to let the rest do their bit. This leads us to consider what forms when matter starts behaving more like material, bending, flowing, hardening, because from here on, we're not just talking about gravity and atoms, we're talking about rocks, rivers, and the beginning of a place you could stand. Earth wasn't always a stable lump of continents and clouds. It began hot, violently, relentlessly, no frills molten. Formed from countless collisions of rock, ice, and metal, early Earth was essentially a glowing mess of partially digested debris. Think less, Garden of Eden, more lava-themed skip. As these chaotic beginnings cooled, heavier elements like iron and nickel sank to the center, forming a core. Lighter materials rose, forming the crust and mantle. This layering wasn't planned. It's just what happens when you mix gravity, density, and time. And unlike flat-pack furniture, it didn't come with any instructions or missing screws. Even today, the Earth's insides haven't fully settled. Beneath our feet, molten rock still churns. Heat from radioactive decay and leftover energy from Earth's formation keeps the interior mobile. The result? Tectonic plates, slow-moving slabs that carry continents, create mountains, and occasionally ruin someone's Tuesday with an earthquake. Meanwhile, the crust, though solid, is anything but quiet. Volcanoes remind us that molten rock isn't far below. Fault lines reveal where the planet shifts. And erosion, driven by wind, water, and ice, steadily wears it all down again. The surface of Earth is in a constant state of renovation, mostly without planning permission. This balance, between the heat below and cooling above, has created a planet with mountains, valleys, rivers, and oceans. None of it permanent. Mountains rise, crumble, and vanish. Oceans open and close, rocks melt, harden, and cycle through the system like particularly slow-moving recyclables. It's not just Earth that does this. Other planets and moons have their own geological dramas. Mars had volcanoes, Venus has tectonic features. Some moons even have subsurface oceans or cryovolcanoes, which sound like they should shoot out icy slushies, but sadly don't. Point is, geology isn't unique to Earth. But Earth's is unusually dynamic. All of this, tectonics, volcanism, erosion, affects more than just scenery. It influences climate, atmosphere, and even life itself. Carbon dioxide can be stored in rocks. Volcanic eruptions can trigger cooling. And mountains can steer rainfall. This leads us to consider what happens when liquid enters the picture. Not lava, but something altogether cooler and more familiar. Water. Because once Earth's crust stabilized and cooled enough to keep water around, the next chapter of change began. One that would reshape the surface in endlessly surprising ways. And that brings our journey to a gentle close. If you're still with us, you're welcome to drift off with another of our sleepy deep dives. Until then, rest well and good night.